So let's consider our third case. So this case addresses when Q of x contains irreducible quadratic factors. What does that mean, irreducible? So irreducible means that the factor that it can't be factored further into linear factors. So an irreducible factor can't be factored further. Okay, and quadratic means it's a degree 2. So in other words, it's something of the form ax squared plus bx plus c, right, because it's quadratic. And it doesn't factor further, it doesn't break down into smaller factors. And one way to tell if it can be factored or not is you look at the discriminant. Which is the part of the quadratic formula that's under the square root, right? So in this case, it's just the part that's under the square root. If this is negative, then it means it doesn't factor over the real numbers. It means that it only factors over the complex numbers. Okay, so that's one way to tell, but for the most part, you can just try it out, see if you can factor it, and if it doesn't factor, then it's probably a irreducible quadratic. And what the rule says is that when we have an irreducible quadratic among the factors of Q of x, then the partial fractions will contain a term of the form ax plus b over that quadratic, ax squared plus bx plus c. So where a and b here are two constants that you need to solve for. So notice it's different. Now we have these two constants in the numerator, not just one constant. So it's like I have this linear expression in the numerator where a and b are now two constants that we're going to try and solve for. Take, for instance, a polynomial of the form x over x minus 2, x squared plus 1, and x squared plus 4. What I notice is this guy here, x minus 2, is linear. X squared plus 1 is quadratic. And you see that x squared plus 1 you wouldn't be able to factor. Same with x squared plus 4 you wouldn't be able to factor. So these are both irreducible quadratic factors. So the form of the partial fractions, well, we'll just have a over x minus 2 for the linear factor, right? Since it's linear, you just have a single constant, a. Now these ones are both irreducible quadratic. So we'll have bx plus c over x squared plus 1, and again is bx plus c because this is an irreducible quadratic. And then same for x squared plus 4, that's also an irreducible quadratic. So I'll have dx plus e over x squared plus 4. Okay, so again here we would have five constants that we would need to solve for to get the full partial fractions. Okay, so we should always look out for this when they're irreducible quadratic, making sure that we have the right form of the partial fractions. Let's try it out with an example. Again, what I notice here is this is not proper. It's improper, right? You guys can see that the degree of the numerator and the degree of the denominator are equal, so that means it's improper. So we have to do long division first. So here I'm going to actually just work it out up here in the space we have up here. So we've got 4x squared minus 3x plus 2. And then we've got divided by 4x squared minus 4x plus 3. Okay. So then 4x squared divided by 4x squared is 1. 1 multiplied by that divisor will be 4x squared minus 4x plus 3. And then we subtract from above, and that gives us down here our remainder. So we'll have minus 3x minus negative 4x, so plus 4x will give me x. 2 minus 3 will be x minus 1. So that'll be my remainder. So therefore this integral becomes 1 plus the remainder, x minus 1, over the divisor, 4x squared minus 4x plus 3. Okay. Notice I don't need to do partial fractions here because it's just one fraction here that's already in its factored form. In other words, this is not going to factor any further. 4x squared minus 4x plus 3 is irreducible. You can check here if you're not sure, but we can tell that it's irreducible by doing the discriminant b squared minus 4ac. So b squared is 16 minus 4 times 3. So that's going to be a negative value, right? So that's 48. So 16 minus 48 would be negative 32. So it's definitely negative there, right? So let's see how we can solve now that it's essentially in the form where we don't need to perform partial fractions. We can integrate the constant term 1 will become x. What I'm going to do here, in order to get this into a form that I can integrate, I'm going to do completing the square on this expression in the denominator. So to remind you, let's remind ourselves how we can complete the square here. So we've got 4x squared minus 4x plus 3. What helps for me is I can factor out the 4 from these terms here. Here I'll put the plus 3 aside. And I want to add something in here that's going to make this a perfect square. And usually I look at the middle term here. I divide the coefficient on the middle term by, so my b, for instance, divide it by 2, and then I square it. So I got negative 1 divided by 2 is negative half, and then squared it becomes plus 1/4. So I'm going to add 1/4 here, and then on the outside here I'm going to subtract the same value, 4 times 1/4. Right? And the 4 comes from the 4 that's in front here. And now this guy will factor into 4 times x minus a half squared. And then out here we've got 3 minus 1, so 2. Now we've completed the square there. And actually maybe sometimes it helps if I were to just bring this 4 back into the squared term here. That's like a 2 squared, right? So this would be 2x minus 1 quantity squared plus 2. Okay, so just doing that little algebraic maneuver now, I'm kind of set up in a way now where I can substitute this 2x minus 1. So let's let u equal to 2x minus 1. So du is 2 dx. So we get a 1/2 du equals dx. So now this integral becomes 1/2 integral, and down here we'll have u squared plus 2. X minus 1, well, let's see, what can I do with x minus 1? I should replace x with something in terms of u. So I'm going to go back here, and if I solve for x in this equation, so I'd have u plus 1 and then divided by 2, give me x. So let's put that in for x here. So it'll be 1/2 u plus 1 and then minus 1. And let's clean this up a little bit. So I'll have 1/2 u plus 1/2 and then minus 1. So that'll be minus 1/2. So I'll have 1/2 u minus 1/2. I can factor out the 1/2 there. So I get 1/4 times, so 1/2 times 1/2 gives me 1/4 there. And then I'll have u minus 1 up here. Okay, so I did a little bit of algebraic simplification here to get there. Okay, so yeah, if you got lost there in that step, just try and write out the details there. What I did was I distributed the 1/2, combined the like terms, and then I factored a 1/2 out from those two terms, and then multiplied it by the 1/2 in front. Now let's keep going. What I'll do next is I'll split up these two into two separate terms. So we got one term u over u squared plus 2, and then another term minus 1 over u squared plus 2. The first term looks like it could be evaluated using a substitution, and the second term looks like it's in the tangent inverse form. Okay, so here I'm going to do one more substitution here. That's substitution within a substitution now. But here I'm going to let u equal to, or I'm not going to call it u now, I'm going to call it w. So we get dw equals 2u. So we get 1/2 dw equals u du. So it takes care of the u du that we have there. Okay, so that becomes 1/2, and then integral of 1 over w dw. This guy, notice this is in the arctangent form, so to remind you here, if I have an integral of the form 1 over x squared plus a squared, this will be 1 over a tan inverse of x over a. So that's what we're going to do here. We'll use that formula to get this second part here. So notice that a squared is 2, so a would be square root of 2. So that'll be 1 over square root of 2 tan inverse of x over the square root of 2. Okay. And then finally we'll just finish up this last integral here. Okay, so with all that, now we've got x plus 1/4 times, here this is ln of w, so 1/2 ln of w, which was u squared plus 2, minus 1 over the square root of 2 tan inverse of, oh sorry, I put x here, I meant u, this is still u, tan inverse of u over 2, u over the square root of 2. Okay. And now, finally, I can put the u back in. Okay, so let's squeeze that here in the bottom. We've got x plus 1/4 times 1/2, 1/8. ln of, let's see, u squared plus 2 becomes 2x minus 1 squared. plus 2 minus, let's see, 1 over 4 times 1 over radical 2, so 1 over 4 radical 2, tangent inverse of 2x minus 1 over square root of 2 plus c. Alright. Okay, well, so hopefully you were able to follow along with each of those different steps. But the process that we went through here is going to be typical when we have an irreducible quadratic like this, where it's in that ax squared plus bx plus c form, where it's not in this like u squared plus 2 squared form. So notice that it involves first getting it into that form by completing the square, and then once it's in that form, then you can split it up into separate terms and do the integration separately. So in the next slide we'll look at generalizing that process a little bit.